And
that's not public yet, but it will be soon.
Yeah,
no, it's public.
It's public, but it isn't made it to a paper.
There isn't like a web page for it. But we don't see extra dimensions, if you would have heard of that. But if we run longer, we'll be more sensitive to seeing extra dimensions. So we don't know how big they are, and if they're really tiny, then we have to run for a long time or get bigger energies. So.
I think the other thing they started looking at is if quarks have substructure, and starting to set limits on that.
Yeah. So anytime we crank up the energy of an accelerator, it's like Rutherford's experiment, right? He took gold foil and shot out what he called alpha particles at it, and he saw occasionally they bounced back like all the way 180 degrees, which didn't fit with the model of what an atom was. At the time, they didn't know there was a tiny nucleus that held the positive charge, but he was able to probe that by scattering the most energetic bullets he had off of the atom. So we do the same thing here. If the quarks are made up of smaller objects inside of them, we have the highest energy beam, so we could potentially see that. Although there aren't a whole lot of hints that is the physics that we might discover. There might be other hints, but could be. So we look at that. We look for deviations from the expected scattering, and that's coming soon. So.
Yeah.
Is there a reason to suspect why if the quark does have substructure? Is there a reason to suspect that?
There's certainly models that have been around like that, but they're not. I wouldn't say there's compelling reasons to believe it, but it's one of these things you check. I mean, anytime you start a new experiment, don't assume what the theorists are telling you is correct. You're doing experimental science. Test all your suppositions.
And we have problems that we don't understand. You take all the physics you know and you put it together. You have things you'd like to explain. Maybe some of the physics we're putting together is wrong when you go to tiny distances. So in fact, extra dimensions is one way it could be quote-unquote wrong. So we're hoping that we'll see a deviation from what we expect, and that will lead us to understanding the new physics. We always talk about new physics. The old physics is cool, but new physics is cooler.
So we did the old physics during the summer. So basically during the summer, we reproduced the standard model and basically measured all the things we expected to see.
So we see the top quark, for example, and there will be results coming in publications in the next month or so from the experiments saying, yes, we see the top quark, and it's produced as often as we would expect in the model. Maybe it'll be, with 10% uncertainty on it, and if we get more precise measurements, we'll find out it doesn't agree exactly. But right now, we see the ingredients of the standard model. We see W and Z bosons. That was something we wanted to see early on, and then papers coming on that too.
So how you said you can verify or disprove that there are extra dimensions exist. What does that like? Can you read that basic explanation? How do you work that?
So the simplest thing you can do is look for what are called Kaluza-Klein resonances. So if there are compact extra dimensions, then the wave function of a particle has 2 bits. One part of the wave function is traveling in the normal 4-dimensional space-time you think of, but the other part of the wave function is traveling in essentially a well potential. It's caused by, and it becomes particle in a box. And as you know, if you have a particle in a box, you get normal modes and excitations. And what would happen is that you would expect to see excitations of, if a particle is traveling in the extra dimensions as well as ours, you should see higher order manifestations of it, higher mass manifestations of it. So you would see a Z boson and at some higher mass, you would see a copy of it. So we can actually go and look.
So like energy conservation can also come into question. The energy we're looking into one of these other dimensions.
It would appear as if could appear as if energy disappeared if it went into these extra dimensions. That then we can't probe again. But what happens is these things exist in the excited state for a while, and then they come decay back to the ground state. So, or the ground state if you think of the particle in a box, the ground state of the particle in the box, then you put an extra node in the wave function, and then it wiggles, or you put 2 nodes and it wiggles. The energy that we're talking about adding there is a big amount of energy because it's a very tiny extra dimension. And so that's the connection to the LHC, is that we know this doesn't happen in lower energies, but if you go to the LHC, you can actually excite the normal nodes of the box, even if the box is really tiny. To have a very curvy wave function means energy. So you're going to show. So the expectation would be, it's like the photon is massless, but the excited photon would act as if it has a really large mass, but that mass is actually the energy in the extra dimensions. And so when it decays, it makes all kinds of stuff.
So here's a plot of muon pairs being produced at the LHC and their invariant mass. And so what I was talking about is, we don't stop looking right here. It could be that other bumps that aren't anticipated start appearing at higher and higher mass.
And notice it's a log scale, so
yeah.
You have only like one event.
So all these resonances you're seeing here, and it's really like doing spectroscopy like you would in any lab. All these resonances you're known. These are all things that have been found before. And if we didn't see them, we'd be worried that our detector was working right. And then as we accumulate statistics, this is going to grow, and this is going to fill in out this way, and we'll search for resonances in that.
So we're hoping we'll see, here's the Z, and we're hoping we'll go out in the tail, and then there'll be something we don't know what it is. Yeah.
And the fact that we're making plots like that and not seeing bumps is already setting limits.
What if this is 500 instead of 100? That's sort of, or 1,000. Let's say 1,000. I think the teletron goes out to about 800, 900. So we're already trying to go out there. So eventually that plot will go, and we'll have, if we see this like we expect, and there's no peak, we can say, there's nothing at 1,000, and we can rule it out.
And then we start
statistics.
ruling out various theories with extra dimensions.
So the extra size of the extra dimensions affects how much extra mass you're going to put on the particle. And if it's really extra dimensions, you should have more. You should go out again and then see another peak, right? The splitting here. You should be able to. If you keep going to higher energy, you'll get.
The splitting will depend on the size of the extra dimensions now. So you couldn't, with just this observation, you might just be making a new particle that decays to muons.
There are other, yeah.
So there's a question.
So how about supersymmetry? And what is theories to expect the peak will be in the
Yeah, so supersymmetry is a lot harder to look for.
Okay.
And the reason why it's a lot harder to look for is because a lot of the energy is escaping an invisible particles. So the lightest supersymmetric particle, something like that. So it's going to take us longer to start setting limits on supersymmetry. And in fact, one of the reasons why we're working on top quark analysis is, okay, new physics might just show up in top reduction and decay. But the other reason is it actually looks a lot like supersymmetric. So if we can learn how to study the top quark at these energies, we actually are learning how to study supersymmetry as well. They're very similar how they decay. But supersymmetry is a harder thing to check.
And again, you might see something that you don't in terms of, we look for events that have lots of missing energy. That could happen for lots of reasons. One, especially at the beginning of the experiment, is maybe you didn't get your calorimeter that has, 100,000 separate little parts to it. Each of them has an adjustable parameter that tells you, if I measure a signal of so many, amps or milliamps or microamps in my detector, that equals some amount of energy. I have to get that calibrated. So there's like 100,000 numbers, or maybe there's 5 parameters. Okay, so there's 500,000 numbers that you have to get tuned right. And if you get that wrong, you have a particle that goes there or goes through a crack, you'll end up thinking there's a missing energy. So to get that as good as you can, people have been working hard on calibrating the calorimeter, which measures the energy. But the other thing that can happen, to illustrate it, is a student last year wrote a senior thesis with me where he was, part of what he did was look at the top quark analysis of how you find the top quark, and then looked at supersymmetric events, and to see how many supersymmetric events would look like a top quark. And the answer was less than than 1% or so. So what that means is if we see top quarks, we need hundreds of them before we might expect one or two SUSY type events. So it'll take a little bit of time since we're now just seeing that we can find top and measure it. But the good thing is like I said, we have 10 times more, actually even more than, that number was 2 10 to the 31. We expect to go to 10 to the 32. So we have a factor of 50 or it's only a factor of 5, sorry, in luminosity, but that was by far the highest luminosity we've ever measured. So.
And they have actually steered the beams into colliding, and we're taking 44.
Yeah, so now our collision rate is 40 times higher than it was when we last looked at it. And you can see the slope of the...
You can see we're collecting events.
So we collected events, and then there was a gap where the green line was at 0, that's the trigger rate, and then you see the green line go way up to 40, and you see the slope of our number of events recorded goes way up, and the area of the gray thing. It's how many events have been recorded since about... Yeah. Time, but reported in the last 10 to 15 minutes.
So
that's a good sign.
We're pulling out of the detector at the moment 40,000 events per second. And each of those events is 380 kilobytes. So, yeah, the data's flowing at a good rate.
Have you given some constraint for the Higgs mass?
Not yet.
Not yet.
No, not yet.
Not yet.
So the best constraints on the Higgs mass currently come from a global fit of all the data, and a big ingredient is actually the measurements of the top quark that are done at Fermilab. Okay. And so, the most likely value of the Higgs mass is around 114, 115 GeV, which is exactly where it's the hardest place to look at the LHC.
But that assumes the standard models, there's nothing else. And there could be, actually, in many models, there's more than one Higgs. So we could find a Higgs this next year.
So you have to look continuously because the prediction is a prediction, and it could just be completely wrong.
But if it's a standard model Higgs, or something that's almost like the standard model, probably we'll be in a race with Fermilab for a while for that.
And while it could be like 5 years.
On the other hand, we have the advantage that we could make heavier particles that are really hard to make at Fermilab, or impossible even to make at Fermilab. And we could see that tomorrow.
I was wondering who decides who writes the paper? Because many people sit on one detector.
Yes. So, for example, on the top analysis that people at Rice are working on, so there's a graduate student, I mentioned a senior thesis last year, a senior thesis this year, and we have 2 postdocs who are working at CERN, who are living there, working. We have maybe about 4 or 5 other universities working with us on exactly the same thing, and the total number of people is about 20, and there'll only be one paper.
So 20 people on one paper?
Yeah, and so what happens...
No, there'll be 1,500 people on one page. Right?
Oh.
Everybody signs.
Right.
Who actually types the words? And actually, what happens actually is somebody might do a first draft, and other people come in. It's a very collaborative process. And even if you wrote the first words, by the end of the process, you don't recognize the sentences as being your own. Because so many people have worked them over in that. And so it's a very interesting process how our papers get written.
But before there's a paper, like our little group of 10 people write a document together, like a super lab report, about 100 pages, with lots of plots and
It's almost like a PhD.
Each person gets their part to it, and they might be the expert on how you measure the missing energy, and they've done the studies. What if the calibration's wrong? How much does that change my answer? They write up. They might have 10, 15 pages there with lots of plots, and then in the paper that's like 3 sentences maybe. But that's the complexity of the experiments we have. On the other hand, the same person, everybody makes the same plots. Like this plot we were showing earlier. If there are 20 people, actually, I would almost argue that everybody on the experiment should be able to make this